Dear students, welcome to 8th lecture of this course. In this lecture, I am going to discuss parametric curves. Before discussion of parametric curves is done, it is important to understand the basic properties of any curve. There are basically three main properties which are important for a curve. One is the chord length. Uh, we will be discussing about details of these properties in the next slide. The second one is the curvature and radius of curvature as well as curvature, which are basically inverse of each other. So we'll be discussing one of these. And the third one is the torsion. And this is important to understand that these three properties are interdependent. Okay, so function of the chord length, curvature, and torsion can be equated to 0. So these properties are also called curves intrinsic properties because they are not dependent on its relationship with the coordinates system. I'd like to explain this with this example. You can see this curve. I can manipulate this curve and move it to another location or rotate it with respect to a common, say, reference point. Its translation or rotation about any point does not change the intrinsic or internal properties of the curve, meaning thereby that its total length is going to remain the same. It's a relationship of the various points of this curve. For example, this point and this point and this point and this point is the same as far as the internal properties are concerned, if we don't look at from the point of view of a this common reference point. So that is why these three properties are also called the intrinsic properties of the curve. Now, coming on to the curvature and chord length, which are the two main intrinsic properties, the radius of curvature can be defined as the distance of arc point from its center. For example, you are having this curve and you find out that within this range of or this portion of the curve, the radius of curvature is like starting from here to here. That means this is the center of curvature and you have this radius of curvature. So reverse of this, reverse of the radius of curvature, that means 1 by rho. If rho is the radius, then k is 1 by rho. So that means the more is the radius of curvature, lower will be the curvature. Okay. So they are inverse because when you see the radius of curvature becomes infinity, means you are talking of the infinite, the length with infinite radius, which is nothing but a line. So line is having very low curvature. That means its points are not varying with respect to each other. So because it is a straight line. So that is why we say that a line is having curvature of 0 and its radius of curvature is infinity. Then you have the chord length. Chord length is nothing but the distance covered along the length of. Suppose I say what is the chord length. I ask you what is the chord length. You will simply say that it is the distance from this point to this point, or from what is the chord length from this point to this point is the distance traveled along this curve up to this point. So curvature can also be defined by in this terms d theta by ds. For example, this one is the angle subtended by this radius on this curve. Then d theta is this angle and ds is the distance traveled. So angle subtended by the distance. Okay, so larger is the distance, lower is the curvature. That means we are talking of, say, typically a large of straight lines. And the moment the distance is reduced, that means you reduce the radius of curvature to up to, say, this circular arc, then ds becomes low, although d theta is same. So that means the curvature is high. So curvature of the low radius, less radius circles will be high, and curvature of the high radius circle will be low. So chord length is simply the distance traveled, and radius of curvature rho is equal to 1 by k. Radius of curvature is rho, and k is 1 by rho. So these are the three properties that we want to discuss. Then just a question to you as a for brainstorming. What is, if you compare these two figures or circles, uh, which one is having low curvature? Okay, so you will can very well answer that the bigger circle is having low curvature, this one is having high curvature. Okay, and which one is having high radius? So this one naturally is having high radius of curvature. Okay, so I often provide an analogy of this curvature with the speed bumps that we often encounter on roads. Okay, so suppose you are having a small bump, but it's very sharp like this, so it is going to give a good amount of jerk to your vehicle if you are driving a car or a bike. And this one, which is although having longer one, but it is having a low, it will provide a low jerk because of the low radius of low curvature, and this is high curvature. So this is an analogy which I wanted to discuss with respect to this curvature and radius of curvature. Okay. Torsion, on the other hand, it is a measure of how much space curve deviates from a plane curve. For example, if this is a helix and it is emerging out from the xy plane at a faster rate, means in two turns it is traveling a distance of say 4 units, okay, or 2 units for example, and this is 0.5, 1, 1.5 and 2. And on the other hand, this helix is coming out of this xy plane at a slower rate because it's having 4 number of turns within this that span. So this means this is having a lower torsion and this is having a higher torsion because this is coming out of the plane at a faster rate. Okay, the rate of travel in the vertical direction is more in this, and rate per unit of this thing distance is less in this case. Okay, so a low torsion here and high torsion here. Now, another important property which can be defined for a curve is the tangent. It represents the straight line that best approximates or clings to the curve near that point. For example, you are having this curve, and on this point, you want to find out the tangent. This is nothing but a straight line which best approximates the point, okay, the adjacent point of adjacent area of this curve about this point, you know. Okay, so this is normal to the radius of curvature. So if you have the radius of curvature, this is the center of curvature, and you have radius of curvature, and this will be perpendicular to this normal. And tangent is found by the, because it is a vector having quantity also, direction as well as quantity, both magnitude as well as direction. So you can find it by differentiating with respect to the parameter u. So suppose you are having a two-dimensional curve, that means only x and y. You have the x parameter value, so you just differentiate with respect to u and differentiate with respect to y. You will get two values, and this is nothing but a two components of the tangent that they will be representing. These are the discussion on parametric curve characteristics. Some of these characteristics we discussed in our previous lecture. Uh, the curve segments, with the help of parametric curves, you can very easily represent curve segments. For example, you want to represent this half circle. So you can see that this is u is equal to 0 here, for example, 1 by 4, 1 by 2, and 3 by 4. So this is starting from u is equal to 3 by 4 and ending at u is equal to 1 by 4. So remember that the direction is also important in this parametric representation that we will see in the next slide also. So meaning thereby you can define the curve segments very easily. The parametric representation is intrinsically dependent. Intrinsically dependent means the relationship between the entities, between the points within the entity is important, is of focus basically. Suppose you are having a rectangle over here, and you want to change its position or rotate it or locate it at a different point or a different location. You can see that the relationship between these lines is doesn't change with the change in the position. So that is why we call it as. So whatever the intrinsically dependent properties, they can very well be defined with the help of parametric curves. Like defining infinite slope is also very easy. So dy by dx we discussed earlier also. It is very difficult to represent a vertical slope because the moment dx becomes 0, in case of vertical lines, it becomes infinity dy by dx. So that is why we define with the help of parametric equation that if the moment dx by du is equal to 0, it means infinite slope. So this is very easy to define with the help of parametric equations. You get more degrees of freedom with parametric equation. A parametric curve can be defined for x and y are different with the help of 4 coefficients here and 4 coefficients here, total 8 coefficients. Okay, and this is why we can have a better control of these curves, and this is easy for transformation also. I'll see in the next slide, because there is a circle and suppose it is at 0 0, you want to shift it to another point. The only thing you have to do is to add the center point in the respective coordinates that you have already seen in the parametric equation of a circle in the previous lecture. Then you have the division of the curve is very easy. Suppose this is a line, you want to divide this into two halves. So you can just say that u is equal to half, and this is going to give you the midpoint. Then direction of the curve is easy to find. In all the geometric representation or geometric modeling, the curves are always associated with their direction of definition. That means they have some kind of a start point and end point, etc. And the transition from 0 to u is equal to 0 to u is equal to 1 in many of the curves, although you use u which may be different from these two values that I have given you, that is 0 to 1, but this helps you to identify the direction of the curve. Like this one is a start point. Suppose you put u is equal to 0, you get a start point, and u is equal to 1, you get last point or end point. So this is how you can define the direction of the curve, or you can understand from the equation what is the direction of the curve. Classification of curves briefly we discussed in the previous lecture. You have plane and space curve, non-form and free form, interpolation and approximation. Let us see. These are examples of plane and space curve. So this is a plane curve, this is a space curve, although it is a line. So, but this is going across x, y, and yz plane. So it is a line which is existing in space or 3D. And here this is a helical curve, which is again starting from xy plane. It is emerging out and going into the space, which is a three-dimensional again. So this is again a space curve. Then you have interpolation and approximation curve. Briefly we discussed in the previous lecture. Interpolation curves, you have the control points and the curve passes through all the control points. In approximation curve, you have the control points, but the curve may not pass through all the control points. It may pass through few of the control points, but not all. So this kind of curve is known as the approximation curve. Then you have the curves of the non-form and free form. Non-form and free form is very commonly used. Non-form is where the curve shape is well defined or defined by its type. Like this is a line, will always be line, and circle will always be a circle. The only thing you can do here is change its center point and radius, nothing else. But freeform curves, which we also call as synthetic curves or user-defined curves, this one, sorry, these are the curves which are defined by the user itself with the help of the providing control points. So the users are perfectly in control to define the shape of this curve. And this one again, the helical helix, this will again fall into the category of the non-form. Non-form is also sometimes called analytical form of equation. Free form synthetic curves or user defined curves, they are kind of this this category where user is the master, user is the controller. And these are the some of the curves equations, both implicit and explicit non-parametric curve equations are given, as well as a parametric representation is also given for line. You can see y is equal to mxc. You all have been studying about this line equation of a line. Then this is again implicit equation of a line, again circle equation, and then you have parametric equation where xc is the center point of the circle and r is the radius. Then you have ellipse, again this is a parametric equation. Hyperbola, parabola, you again have these equations you already know, and this is the parametric equation. Circular helix, it is very difficult to define with the help of non-parametric or analytical equations, but very easy to be defined with the help of parametric equation. And see, when you say u varies from 0 to n, so n typically here means so here the equation should start with n. You have to add n in this equation over here, n into h into u. So that means the number of turns of the helix. Suppose you have two turns, so you will say 0 to 2. Okay, because okay, so more details we can discuss in our tude section. Thank you.